Hello and welcome to the next problem in our series in quantum mechanics. So in this problem we're going to be looking at a particle in what's called the infinite square well. So this is a famous problem in quantum mechanics, and it's really kind of a toy problem because there isn't really anything that's quite exactly like this. However, it really is it serves as a good example. Many problems can be almost approximated by this. In fact, actually, for my when I did my PhD, I worked on a problem that was effectively a real physical system that was effectively this. And namely, what it is you imagine that you have a place where an object can move back and forth, but it can never go beyond this region between x equals 0 and x equals a. And so what we say that the potential goes to infinity, so it's going up to infinity here. And then in between x equals 0 and x equals a, there's no potential. So it's just a free particle moving back and forth. So the classical analogy to this is imagining you're stuck in a canyon, and maybe it's like a frozen ice canyon, so there's like no friction, and you can just go back and forth, and you just hit the one side of the canyon and the other side of the canyon, and you're just moving in one direction. So it's like a little narrow channel. So if you put a quantum mechanical object in this channel, some interesting things happen, and that's what we're going to set up and try to get to as much of in this video, and if not in the next, if we don't get it all the way, then we'll get to it in the next video. So first we do is we write down Schrodinger's equation. By the way, remember that this is a potential that doesn't vary in time. The potential is just fixed, so we can use Schrodinger's time independent equation. So we've gotten rid of the time factor. So that equation says that minus h bar squared over 2m, so it's a particle of mass m. Well, the wave function describing this particle has to obey this equation. Okay? Okay, so what we can do first is we can simplify. Let's just make this substitution. We're going to say k squared is equal to 2me over h bar squared. Okay? So what that does to our equation up here is it makes it d squared psi dx squared is equal to minus k squared psi. So this is a differential equation on the wave function psi, and this is actually a simple classical harmonic oscillator. You may have seen this in many other problems you've done in the past in physics. So the solution to that equation are sines and cosines. So in general, the general solution is, solution to that equation is psi of x is equal to a cosine of kx plus b sine of kx. Okay, let's just check that this works. So d psi dx, which we often write as psi prime, that's equal to minus k a sine kx plus kb cosine kx. If we do the second derivative, so psi double prime, d squared psi dx squared, well, again, we get a factor of k out and another factor of k out. So this becomes minus k squared a cosine of kx minus k squared b sine of kx. Okay? Remember that derivative of x of cosine of x is minus sine x, and d dx of sine of x is cosine of x. And then if you have a k, you bring that k out. Okay, so look, this is in fact minus k squared times psi. So indeed, this equation satisfies that differential equation. Okay, so now the question is, what wave function will satisfy or what set of wave functions will satisfy the boundary condition. So that's the key in a lot of a lot of problems. So our requirements, and we can even color code it back to the orange here. Our requirements are that psi of 0 has to equal 0. So by the way, I should kind of give you a sketch of what the wave function will look like. The wave function has to, we said that there's infinite potential, so the particle can't penetrate here. So in fact, if you were to plot the wave function is 0, or technically it's plotting the probability. So the probability is like psi squared. And then it's going to do something in here, and then again it's going to go to 0. Okay. So by the way, if you were to add up all of the square of the wave function in between here, remember that the wave function describes the probability of finding the particle. So it has to satisfy the condition that psi squared integrated from 0, or actually integrated from minus infinity to infinity, that has to equal 1. So so in fact, the integral from 0 to a has to equal 1. Actually, that's going to be very important when we try to determine what the coefficients are. But first, let's just look at the boundary conditions at this point here and at this point. At this point, the wave function has to go immediately to 0, and similarly at the other boundary point A. So that means that psi of 0 has to equal 0, and psi of A has to equal 0. Okay, so that means that 0 is equal to A times cosine of k times 0, it's cosine of 0, plus B times sine of 0. Well, sine of 0 is in fact 0, and cosine of 0 is 1. So in fact, we've now just determined that A is equal to 0. Okay? So we don't have to worry about, the way we've set up this problem is we only have to worry about the sine values. Okay? So let's look at the other boundary condition. So psi of A is equal to, we already know that A is 0, so we don't have to worry about that. Cosine of Ka plus B sine of Ka. So we now have, so this has to equal 0. So either, I'll just write that, either B equals 0 or Ka is equal to n times pi, right? Because sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, etc. Well, let's go back to this problem, this solution. If B is equal to 0, then we're left with psi is always 0. So that works, that satisfies the differential equation, but the reality is that doesn't represent, or rather it doesn't represent a physical reality, because that means that the wave function is always 0, and our requirement is that for something to be physical, it has to actually have a probability of being somewhere, and namely the probability of the particle even being somewhere, overall space has to equal 1, whereas if you had this solution, the probability of finding the particle is 0, so it's not even a physical solution. Okay, so we've now set up the situation so that our solutions are going to be our solutions are such that k times a equals n over pi. So actually, let's wrap this up. I only have a minute left. So the one thing I want to point out is that, remember when we did our substitution for k up above, k squared is equal to 2me over h squared. So in fact, our energy, I think I might run out of time, so we might have to do this in the next video, but our energy is equal to h bar squared k, and there's many solutions of k squared, over 2m. So that equals n squared times pi squared times h bar squared over 2m a squared. Okay? So quite interestingly, the lowest value of the energy is when n equals 1. So actually, I'm going to stop there, and we've just now solved what the energy values are. We've determined that there are many solutions, and we're going to discuss this in more detail in the next video. So I'll see you in a minute.